and welcome to our October meeting. We're glad to see you guys here. It's a smaller crowd tonight, but we know there's others watching online. And we're just talking about the eclipse. Laura, I don't know if you want to put in the chat if you were able to see the eclipse or not, or what you were able to see. But I know it was cloudy where Vic was, and Chris was unavailable. Oh, who else is? Anyhow, so tonight we have Brian Mendez talking to us about the ionosphere and the icon mission. And sometimes I mash the two of them up together and call them the iconosphere. We know just the ionosphere is such a unique part of that. I often think of it as interspace because it's not really atmosphere and it's not really space, but that really unique part of our that space in outer space. We'll be talking about the icon mission and sharing resources with us, and then we have a little bit of community news for you. And but I would introduce Brian. I should have asked you for Brian. Brian works for the Space Science Lab at UC Berkeley in the multiverse, and he is an astronomy educator. He is also a music. He's got a degree in music, I know that, and also teaches astronomy classes there at UC Berkeley. Is that correct, Brian? Yeah, awesome. So, well, welcome, Dr. Mendez.
Well, thank you. So, I'll start out by telling you that I'm going to tell you about the ICON mission because it's one of NASA's latest missions that was selected just a year and a half ago, I think, maybe 2 years ago now. And it is being built here at UC Berkeley, or actually it's probably being built at a number of places, but some of the instruments are being built here, and the PI is here at UC Berkeley. So I get to speak about it often. The missions at NASA no longer have the education programs associated with them the way they used to. So we do have a person here who's kind of in charge of communications for ICON, and that's Claire Raftery, who I believe you all know pretty well. But Claire is right now on an airplane flying all the way around the world, so she couldn't be here right now to talk about ICON, so she left it in my hands to speak to you about it. I also wanted to try and get the ICON PI, Tom Immel, here, but he's also in transit. Busy day for ICON people, I guess. So I'm going to tell you about the mission, and I'll also show you an activity that I came up with last winter to do a simple demonstration about how to understand the ionosphere and where it comes from. And of course, as is always the case with me, I welcome anytime you have questions. Just go ahead and interrupt. Don't wait for a pause. If something's curious to you at the moment, then let me know. So I'm going to show you some slides about the ICON mission, and then after that I'll talk about that activity. So let me bring up the slides, and then I'll share screen. I just realized I may need to. I have a double monitor thing here, so when I share the screen, good. Can you all see the full screen slide? Okay, good. Sorry, that's the wrong one. There we go. All right, so as is always the case with NASA missions, ICON stands for something. And ICON is short for the Ionospheric Connection Explorer. Explorer is not actually part of the the acronym, but Explorer is a class of NASA satellites. So it's going to be looking at this place that is a boundary between Earth and space, and it's going to be trying to understand some physics that are happening in the ionosphere that have been very poorly understood and only known about since the dawn of the space age. And the reason for the picture in the background here is actually because this is a shot from the International Space Station. So you're seeing lights from city underneath, and you're seeing some of the glow of the atmosphere above it in a few different colors. You see yellow, kind of a aqua color, and then above that a red color. And this is all air glow that's somewhat analogous to the aurora, but it's in that its physics are similar, but it's not the aurora. So you're actually not seeing auroral glow here, but you're seeing air glow from another process that we'll talk about in a minute. So there's a movie that I'm not sure how well will play over the internets, but I'll go ahead and let it run here. It'll probably be somewhat choppy depending on your bandwidth. But this is, again, footage from the International Space Station flying over equatorial regions of Earth. So at some point here, I think we're over India and Pakistan. You can see lightning going off there, the tops of those thunderheads. And you'll see a very strong glow of air that's, again, in those three colors. There's some yellow, there's that aqua, and then there's the red glow above. And again, this is over equatorial regions on Earth, so we're nowhere near the poles. And I should say that this air glow is very dim and really not visible to the unaided human eye. You need cameras, and so this is, the cameras here are seeing this with their greater sensitivity than the human eye can see, and this is not visible from the ground. No one has ever seen this emission from the ground on Earth. And you can see that there's something drawn in here. The ICON mission will actually be especially interested in observing that region that's where you see all the red glow. Okay, so let's do a brief talk about where the ionosphere is in relation to the rest of Earth's atmosphere. So in some sense, it's the outer regions of the Earth's atmosphere, but it's not like you go, troposphere, stratosphere, thermosphere, mesosphere, and then ionosphere. There, in fact, is an overlap of regions between the ionosphere and the neutral atmosphere. So the neutral atmosphere and the ionosphere actually overlap for a region of the atmosphere. And the ionosphere itself is fairly dynamic. Most of it is created by solar radiation. And in fact, most of the energy that creates the ionosphere comes from the ultraviolet light of the sun. So that means that the day side of Earth has a fairly thick and well-structured ionosphere. The night side of Earth has a fairly weak ionosphere that's almost not there at all. And most of the radiation that's producing the nighttime ionosphere is coming from cosmic sources. You'll notice in the picture here that the regions of the ionosphere are kind of divided into several lettered regions, E, F, and D, and then the F region even subdivides into 1 and 2. I couldn't tell you off the top of my head what those regions specify, though I'm sure that I'm pretty sure that they have to do with the densities of the ions that they are seeing in those different regions. So here's just another slide that explains that again. The picture, I think, is actually the most useful thing to look at because it shows you that overlap that I was talking about. So, if you think about the Earth's neutral atmosphere as starting with the troposphere that's right there at the surface and then going all the way up to the thermosphere, then the ionosphere overlaps the neutral particles starting from about the top of the mesosphere upwards. So the D region is also in common with parts of the mesosphere and the thermosphere, and then the E and F regions are sharing space, if you will, with the neutral particles in the thermosphere of Earth's atmosphere. Now, the particle densities up there are really, really low, but still interesting from our perspective on Earth. This, I think, just says in words or in text, what I had told you in the previous picture about the ionosphere being mostly created by UV, and also that it shrinks and grows depending on whether or not you're on the day side or the night side of Earth. Here's a nice little graphic that kind of demonstrate this in a grossly over-exaggerated way. The scale here is way off, but it's to give you this sense that on the day side, you've got a lot more thicker ionosphere above ground than you do on the night side. All right, and this just kind of further illustrates that. So if you pick a point on Earth and you watch it kind of, so in some sense, the ionospheric shape itself maintains its shape relative to the sun, and it's a place on Earth that's rotating underneath that makes kind of the ionosphere appear to thicken and decrease as you're moving.
Brian, did you see Vic's question in the chat?
I didn't see it. No, can you tell me?
Yeah. So he's wondering if the sprites go through this region, and how much of a block to UV is accomplished by the ionosphere?
So the sprites, I think, are still pretty far down. So let's go back. I think sprites still occur, I believe, in the stratosphere. They may extend up into the mesosphere, but I think for the most part, sprites are down there in the upper part of the stratosphere. So yeah, so we're talking about something that's that's above that region. Yeah.
So some of the reports that they say that the sprites reach the ionosphere and charge it are actually incorrect.
Well, so I'm thinking that sprites, from what I understand about them, they can reach almost that region where you can see actually this on the right hand part of this graphic. It shows that the aurora, for example, happened at the top of the mesosphere and within the E region of the ionosphere. And sprites, I think for the most part are happening just in the layer underneath that. So within the mesosphere. So maybe the energy from them could be injected upward, but they're not necessarily coincident. And then there was a second part of that question, right?
If the ionosphere is absorbing the UV, what kind of shield does it perform? Does it perform as dramatically as the ozone, or is it just very minimal?
Well, it blocks a good portion of the UV, and it blocks almost all of the extreme ultraviolet. So when we think about, often when we think about UV in a human standpoint, we think about this, we break it up into the A, B, and C parts, right? There's UVA, UVB, and UVC. And UVA is the part that's actually somewhat good for you in the sense that causes your skin to tan, and it causes your skin to release vitamin D. UVB actually causes burns, and UVC is actually pretty lethal. And UVA is mostly it's some of it reaches the surface, obviously, because we get tanned from it. But the ozone layer is responsible for kind of mitigating most of the UVA and the UVB. But the UVC, for the most part, is stopped by the ionosphere. Although when we talk about the activity in a couple minutes, we kind of come back to the idea of the ionosphere. The ionosphere, in a sense, is a shield for the UV, but it's weird because it's a shield in the sense that it's made because it's absorbing all that UV. It's really the atmosphere that's the shield. It'll be more clear when we come back and look at that activity as to how that works. Good question, thank you. So let's see, I was going to move on to this slide to talk a little bit about actually energy injection from below. So the sun obviously is creating is doing the ionizing of the ionosphere. but there is also energy that comes from below that'll push on. We'll talk about the Earth's magnetic field in a minute, but energy from the neutral particles that can be carried by heat sources that are happening below will interact with the ionosphere, right? Because those neutral particles and the ionized particles are sharing space, they can still interact with each other through normal gas interactions, right? So there can be particle collisions, and pressure and temperature, any kind of acoustic wave, for example, that's passing through the neutral particles can be imparted into the ionized particles. And the real difference, of course, then, is that the ionized particles also will respond to electric and magnetic fields, whereas the neutral particles won't. So one of the very interesting things is heat from weather can be transported upward into the upper parts of the atmosphere, which also will inject energy into the ionosphere as well. And we'll come back to this. This picture is pretty important. The fact that you have 3 fairly large continental bodies over the equatorial regions, and that those are places where thunderstorms typically happen, is kind of important. So Earth's weather actually will inject some energy into the ionosphere. So here's a little reminder about Earth's atmosphere. Close up, it looks kind of like the dipole of a magnet. And if you zoom in, and there's the sun, just for reminder. You zoom into the magnetic field near the equatorial parts of Earth, which we often haven't been thinking about a lot because we're always interested in the aurora, and so the poles are kind of interesting. But near the equator, you realize that the magnetic field lines actually kind of form footprints that are almost kind of reminiscent of, well, for me anyway, reminiscent of the footprints that we see in the sunspot regions in the sun. But if we kind of zoom in, here's a little graphic to make us think about. So if there's heating from below in the neutral part of the atmosphere, that heating transfers energy upwards and creates kind of a fountain, right? So it's going to push particles upward into the atmosphere, where it'll carry heat anyway, which will create currents that travel upwards in the atmosphere. And then those currents are going to rise up, and then they're going to fall down. It's basically a convection current, right? You'd expect kind of this vertical convection current to happen. The lower part of the Earth is getting heated, and it'll carry heat upwards, and then it'll fall back down in a vertical convection cell. But the trick is that when that energy is transported into the ionosphere, those charged particles, when they fall back down to Earth, they can't fall just any which way because they're charged. And so they're actually going to see that magnetic field of Earth, and they're going to get stuck to the magnetic field lines, and they're going to fall along the magnetic field. So when they fall back to Earth, they're actually going to fall back and impact the upper atmosphere in a similar way to the way the particles fall along the magnetic field near the poles and create the aurora. So this is where we think the air glow comes from. It's coming from the particles that are being that are channeled along the magnetic field lines and then actually accelerated along the magnetic field, hitting it and creating air glow that's the same physics that happens in the aurora, but at much lower densities and therefore much lower light intensity than the aurora. So if you just forget about the structure of the Earth's continents or anything, if you just kind of imagine this idea of a fountain, then your expectation for what the air glow would look like in space would be the top picture, right? So the top picture would just say, okay, we've got these convection currents coming from the surface. They're driving. They're going to be strongest right at the equator because that's where the sun's heating of the Earth's surface is strongest. And then they're going to fall along the magnetic field, and we should see kind of a binary band across the Earth. These dips here are actually due to the structure of Earth's magnetic field. So that's what we would expect, just forgetting all other things. The reality is what we see below, and actually the this is still not actual real observations. I believe those are still models down here. But the reality is that we actually see stronger emission coming over the continents. And the reason for that, as I alluded to in the previous slides, were the fact that the continents cause thunderstorms, right? So you get a lot of you have a lot of moisture that's hanging around in the tropical regions on the planet. That moisture is picked up off the oceans, and then when the air currents carry it towards the land, you get a phase change in the water and you get thunderstorms. And whenever you have a phase change from the gaseous state of water to the liquid state, you're going to get a big release in heat. So that big release in heat that happens during the thunderstorms moves up in the atmosphere and creates additional energy in those convection currents. And so you get effects over the continents. So the weather on Earth actually can change what's happening in the ionosphere and these fountain currents. So it's pretty cool, right? You've got energy from the sun injected into the atmosphere, and you've got energy from thunderstorms coming from below, and they create the physics that are happening in these fountains. So one of the taglines, in fact, that we were going to use for ICON was where Earth's weather meets space weather. So I mentioned earlier that this has only been known about since the space age, since we first put satellites in orbit and could look back and actually see the emission in the ultraviolet, in fact. And so there's a picture from the Apollo 16 that actually saw some of that emission on the night side of Earth there. So you got the day side is the big bright stuff, and the night side there is where you see this equatorial air glow caused by this fountain effect. And then there's the image satellite seeing the night side of Earth and seeing the double banded glow around the equator. So the physics in here are actually fairly complicated, and people haven't understood the ionosphere for very long at all. One of the things that I like to tell people when we tell them about this mission is that when I first heard about this mission, I was listening to the PI of the mission, Thomas Immel. He was giving a talk here at the Space Sciences Lab, and one of our Nobel laureates was in the audience and was actually sitting right next to him, Charles Townes, who just passed away this year. Charles Townes is, inventor of the laser, and that's what he won the Nobel Prize for. And he was sitting there, and he was asking a bunch of questions at the end of Tom's talk, and then he kind of muttered to his colleague next to him, and I overheard him say, he's like, "Wow, this is really complicated stuff." And so, if you ever find, and so I always, think that's important, because if you ever find yourself thinking, "Wow, this is really complicated," well, you're in good company, because Nobel laureates agree. So here's some fun models of what the dynamic, how dynamic this air glow could be, depending on what's going on with both the weather and the sun. So this is why it gets so complicated, right? Because now you've got two fairly complicated inputs of energy, the weather and the sun. And so these are just some fun models that they have created to try and input all of the information they can and predict what should be happening. So they call this the planetary weather dynamo, and the goal of ICON is basically to understand how it works and be able to predict it. One of the reasons that it's important to be able to predict is you get these large flows of ions in the upper atmosphere, and those can change the way, especially radio signals, are traveling through the ionosphere, or through the atmosphere itself, right? So we've got a satellite up there that we're trying to talk to, and all of a sudden there's a big storm in South America. It's creating a giant blob of ionic particles that are moving across the Americas. That's changing our ability to talk to that satellite, which, especially if it's, say, a communications satellite, or say it's a navigation satellite, one of the GPS satellites, you can actually, because of the attenuation of the signal, you can end up with errors in the positioning system that give you a few meter, can add up to several meters. And if you're trying to do something precision with GPS as opposed to maybe just simply trying to find your way to target when you're in an unfamiliar town, right? But say, the military is especially interested in this because say they're using GPS to fly one of their drones. Well, a difference of meters can make quite a big difference and be an important impact.
Brian, Vic wants to know if the ionosphere is more or less not moving, but the motion is due to the spinning of the Earth.
Yeah, so it's moving insofar as, as Earth is going around the sun, it's moving with Earth. So it is still kind of moving around in 3D space, but relative to a sun-Earth line, it's staying fairly, its shape is then kind of fixed with an Earth-Sun line.
So in other words, if we had, for example, a satellite right over this bulge right here, within an hour, is the bulge going to move because it's going to follow with the planet, or is the bulge going to stay here and just go away?
Are you talking about the bulge that's, say, like at the subsolar point that's underneath the noon? Which slide are you at?
I'm looking at the one you have on right now.
Oh, this current slide. So okay, so these bulges actually, yeah. So these enhancements are due partially because of the continents. So they will actually move with the continents. But you do get an enhanced effect from the fact that, okay, if you're on the day side, it's going to be stronger than if you're on the night side, right? So it is complicated by the fact that, okay, part of it's going to move with the continents, and then part of it's going to stay put relative to day and night. So exactly how big the enhancement will be will depending on, okay, are there thunderstorms happening on the continent, and what time of day is it? And what's the amount of solar activity at the time? So all of those things will play into how strong those blobs will end up being.
Brian, is there anything significant about the two different bands?
So one is north and one is south, right? Because the magnetic field has that, has the both poles.
So how come they come together in some places? Or do they start together and then come apart?
Well, the bands are so if you look on the left side here, they always kind of stay apart. They dip around because of the shape of Earth's magnetic field. Earth's magnetic field is not perfect. It's not that perfect dipole that we think of, and it's a little bit offset, so it's not completely aligned with the Earth's geographic poles. So that's why there's a bit of a dip over the Americas. But the northern band is following the magnetic fields kind of northward of the equator, and then the southern band is following the particles that are falling back along the magnetic field toward the southern half of the equator. Does that make sense, Ricky?
Mm-hmm.
Okay.
Brian, Laura had a question about, she said this possibly related to the newer idea that some terrestrial storms could be connected to solar weather events, or which came first type situation, solar, terrestrial, ions, magnetics, lightning?
Oh, so I guess, so it sounds like you're asking if solar events can affect the weather. That, I don't know anything about that. I'll just say that. I'll say that what we're looking at here is a part of the atmosphere that's affected by both the weather and the sun. And I think it's probably an open question as to whether or not there's any path of influence kind of backwards along that path. At first glance, I wouldn't necessarily expect there to be, but that's just, I'm not an atmospheric scientist either. It's just my basic physics background kind of making me think that I wouldn't see the energy flow from the sun necessarily going back through the ionosphere, although, they're connected, right? So energy that goes into the ionospheric particles are sitting there um, with the neutral particles, so they can inject energy into the neutral particles too. But then whether or not that energy is going to make its way back down into the troposphere to affect the weather, I don't know. My sense is that direction of energy flow isn't as easy to make happen. But that's just my guess. I would say let's read more about that.
That's awesome.
Any other questions?
She said that there's a study that is being looked at and debated in meteorology groups. I was wondering if they could be connected.
I mean, of course, the sun obviously has a huge influence on. I mean, it's the driver of all weather on Earth. So, but that's the visible part of the spectrum, the part that isn't as affected by space weather. When we think about space weather, I'm usually thinking about ultraviolet X-ray, that kind of energy injection. And of course, there's particles. The particles, they don't even reach the atmosphere, right? The particles all get deflected by the magnetic field. So, and then we will talk about, so it definitely does affect the ionosphere. So I guess it's how much interplay there is then between the ionosphere and the neutral particles, and then how much that energy can be transported down deeper into the atmosphere. All right, here's a fun little animation of how ICON's going to work. So ICON is going to be interested in trying to study that air glow. So it's going to have it's going to have what we call in situ instruments. So those are instruments that can sense the electric and magnetic fields that are at the spacecraft's location. And that's useful because, as you can kind of see, when the spacecraft is passing over the equatorial regions, when it's going through the magnetic field, in a sense, then it's connected to that magnetic field line that's both there in space and also that field line as it goes down into the atmosphere. So you can have a sense of what's happening along the magnetic field, the whole line. So you'll know something about the north and the south field as you're passing through one part of it. And then it also has these imagers which are going to be able to look at the air glow, and it's not going to be making like a 2D image. Instead, it's going to be making spectra. So the imagers are actually spectrographs. So they're going to be looking at the spectra, trying to understand how the interactions of the particles are with. And so basically, you're going to be looking at the ionospheric particles as they're hitting the neutral particles, exciting the neutral particles, and the neutral particles will glow and give off the air glow. So we'll see the light from that glow from the neutral particles after they've been excited by the interactions with the falling ionic particles. And you can see that the spacecraft is going to do this little dance where it'll kind of rotate around. So it'll, at one point, it might be looking at just the northern part of the fountain, and then it can also swing around and look back and see both parts.
So Brian, Vic had another comment. He said, ham radio operators use the ionosphere to skip signals around the Earth. Where does this occur, and how does it affect the frequency of the reflected wave?
Yeah, so ham operators aren't the only ones. Anybody who's doing any kind of radio communications over the horizon has to use the atmosphere to skip their signal. So aircraft are doing this, and when they're doing ship to shore, if you're communicating with a ship at sea or a submarine or anything that's over the horizon, and you're doing communications and you're not using satellite communications, then you're going to have to skip off the ionosphere. So several radio wavelengths are kind of the atmosphere, or the ionosphere looks like a mirror to it, and so you can kind of bounce them off. And what happens is when the ionosphere gets enhanced, it will often deepen the D layer, that bottom layer, which will change reflective ability and often causes a lot of radio interference. So a lot of and I say it seems that sometimes you can actually end up getting a farther skip when the ionosphere is enhanced than you can when it's when the ionosphere is not as enhanced. This seems to be my memory of the friends I have in. Oh wait, Chris, you're a ham operator, aren't you? Did I recall that from a previous conversation? Are you still around?
It looks like he's stepped
Oh,
away.
he stepped out. Okay, well, when Chris comes back, let's ask him if when solar storms are happening, if he can talk farther or shorter distances when.
Okay, I'll put that in the chat and we'll ask when he comes back.
Yeah.
What I was told, I was talking to a ham operator up here, is that as the storm occurs, the frequency at which they can transmit changes successfully. It seems to be as it becomes more and more enhanced, shall we say, the frequency at which you transmit changes.
Right, and so I guess that would be in the sense that, yeah, okay, so then it's changing the properties of the ionosphere so that, it's opaque at a different frequency. Because then basically what's happening is if you're transmitting at the same frequency and the ionosphere has become transparent at that frequency, then your signal just goes straight off into space and doesn't bounce. So you have to switch up. Okay. Oh, this last slide is just an email that went back and forth between Tom, the PI of the mission, and one of the astronauts aboard the ISS at the time, who was taking some of these pictures and actually, in some sense, not quite gathering data, but they, those the astronauts, they really love the photography. They kind of have become, a lot of them end up becoming like amateur photographers because it's just so amazing, the views up there. But some of them have become especially interested in the air glow and have been gathering a lot of pictures and then sharing them with Tom, so Tom can try to actually see if he can figure some science from them. Okay, so that is just the talk about the mission. So are there any other questions about the mission itself or this crazy phenomenon of the equatorial fountain?
I like the idea of an equatorial fountain. That's great.
Okay. Well, then the other thing I wanted to show you.
I do.
Oh, go ahead. Yeah.
You're talking about convection currents carrying up the heat.
Yeah.
Into the atmosphere, correct?
Right.
Well, convection implies there is matter carrying the heat. But as you go up in the atmosphere, your matter becomes almost non-existent. So
yes.
How can you carry heat when there's almost nothing there?
Well, so then you get into a place where, I don't know if the atmosphere ever gets quite collisionless. There's different physics, and when you talk about collisional gases and non-collisional gases, kind of different physics will come into play. I'm not sure at what point the atmosphere becomes quote-unquote collisionless. You can still carry heat that way, but then the collisions that you're dealing with are they become more like what we call Bremsstrahlung. It's a type of collision, but it happens through the electric force, and so then the electric force is transmitting the energy. But once you get to very low particle density, energy transport becomes a little less efficient through matter. Becomes more efficient through radiation. All right, let's look at this activity that I had put together, and I haven't actually published it anywhere, so you're seeing it here, and then I guess we'll put it on the Wikio, and you can get it from there. I've got it written right up now as a PowerPoint slides, and you can take the slides and then change them as you need to. So I start off with actually a review of Earth's atmosphere, so we can talk about just your question there, Vic. We can look at how the atmosphere is changing with altitude. One of the reasons I liked this graphic on the left-hand side here is because it gives you a sense of where are some things we know about in these different parts of the atmosphere, right? So start with the troposphere down at the ground. This is the part of the atmosphere that we live in. This is where most of the mass of the atmosphere is. So 80% of the mass of the atmosphere is in the troposphere. All the mountains are in the troposphere, so Mount Everest, airplanes are flying around for the most part down here. Then above that's the stratosphere. So that's where the ozone layer is. This is where, highest flying commercial aircraft might go, but really commercial aircraft for the most part hang out in the troposphere. It's only kind of military that might go up in the stratosphere. Of course, Sophia goes up into the stratosphere. That's the NASA's infrared telescope that's aboard a 747. So almost most of the remaining mass in the atmosphere is here in the stratosphere, so about 19%. So if you're doing the math, that leaves only like 1% for the rest of the layers of the atmosphere. One of the things that's also kind of interesting is part of the way that you can define these layers of the atmosphere is by the change in their temperature gradient. So whereas pressure is always decreasing as you increase with altitude, and mass and density are always decreasing as you increase with altitude, temperature is the one thing that actually keeps changing its direction. So in the troposphere, as you go up, temperature decreases, but then it stops decreasing and actually turns around, and that kind of marks the boundary then between the troposphere and the stratosphere, because then in the stratosphere, the temperature starts to go up again. And then you reach another boundary where temperature stops, turns around, and begins to cool off again with altitude, and that's where so that demarcation is the line, the boundary between the mesosphere and the stratosphere. And then that happens one more time where it turns around and then the temperature starts going up again, and that's where we call the thermosphere. And it's useful then to actually, when you're talking about that with students, to maybe even go back and remind them about how temperature and heat are kind of different. They're totally different ideas, right? Temperature is this measure of how much kinetic energy the average particle in the gas has, right? Whereas heat, well, technically heat is heat is a verb. Heat is how you inject thermal energy into something. So think about the thermal energy of the total thermal energy of the atmosphere up there is pretty low because the density is extremely low, right? So average particles may be moving around with a lot of kinetic energy, but there's very few of them. So the total thermal energy that you have in a parcel of gas in the thermosphere is very low compared to the amount of thermal energy you have in the same volume of gas in the troposphere. The analogy that I always use is think about boiling water on the stove and air in the oven. So let's say you're cooking some cookies at 400 degrees in the oven, and you're going to boil a hard-boiled egg in a pot of water on the stove. So the pot of water on the stove is boiling at 212 degrees Fahrenheit. The air in the oven is at about 400 degrees Fahrenheit, right? So the temperature in there is much hotter, yet you'll regularly reach your hand into the stove to grab a cookie without thinking about it, right? You just grab that cookie. Whereas you would never consider sticking your hand straight into that boiling pot of water to grab the hard-boiled egg. And that's because density, right? It's because of the density. It's not because of the temperature. The water has so much more thermal energy because it's so much more dense, even though the average kinetic energy of the particles in the water is lower than the average kinetic energy of the particles in the oven. There's my little aside. Okay, so
Made it really nice and simple. That I can teach to my freshmen.
good. Here's just a review of these. So we already went through this in the other slideshow, but this you can show to your students too. Just a reminder of where the ionosphere is then in this whole scheme. So it's up there overlapping with the mesosphere and the thermosphere, and its structure changes with day and night. And I have that little bit that I mentioned earlier, the fact that one of the big difference, of course, is the ionized particles can respond to electromagnetic fields, whereas the neutral particles don't. Now, here's another piece of important information that, hopefully is review for students. Just how does light interact with matter? So, a lot of students, when they learn about spectra, they'll learn about this idea that, an atom or a molecule can only absorb photons of a specific frequency or a specific energy. And they can then change energy levels within that atom or molecule depending on the energy that they can absorb. And actually, it turns out molecules can also absorb photons that don't change the electronic structure, but they actually can change the rotational or vibrational modes of the molecule. But it's the same kind of idea, is that those energy levels are quantized, and so you can only absorb a photon of a specific energy. But as it turns out, that's only true within a certain wavelength of photons. So infrared, visible, and near UV photons, they'll all obey this law. They can only specific energies can be absorbed. The other ones will be kind of ignored by the matter. But when you get above a certain energy threshold, extreme ultraviolet, X-ray, gamma rays, every single one of those can ionize a particle, right? So they can go in there and they can knock an electron straight out of the molecule or the atom. It doesn't matter what energy they have. They come in and they're going to knock an electron off. Okay, so here's the activity that we do. So we turn the classroom into Earth atmosphere, choose one side of the classroom to be the ground, then the other side will be space. Make about then, say, 2/3 of the room is going to be the atmosphere, and maybe 1/3 of the room is going to be empty space. And you're going to divide up the class. Half of the class are going to be gas particles in the atmosphere. The other half of the class are going to be photons who are going to enter from space and move toward the ground. So then I'll show you the cards that they're all going to get here in a minute. You're going to give the gas particles cards, and the gas particles cards are going to tell them where in the atmosphere they hang out. So are they in the troposphere? Are they in the stratosphere? Are they up in the mesosphere? And it's also going to tell them that they can absorb photons with very specific energies. And so it's going to give them a list of which energies they can have. And so the example I have here is, it might tell them you can take 1 or 2 or 2.5 or anything bigger than 12 electron volts. So the energy that I use here is the electron volt. That's the energy unit that I use. So they can grab, specific ones, or they'll be able to grab any one that has higher energy than that 12 electron volts. So they're going to be dispersed in the atmosphere, hopefully according to what the card says they should be closer to the ground or farther away from the ground. And then the photons are all going to get a card that just basically says, here's what type of photon I am, and here's my energy. And they're just going to kind of hold that to their chest. And then the photons are going to walk across the classroom toward the ground from space. And the gas particles are going to reach out and grab any photon that has an energy that they can grab. So they have to ignore ones that don't have the energy that they can grab. And of course, if it's a case where it's a really high energy photon, well, then any one of them can grab any one of those high energy photons. So pretty simple demonstration. Have them do it, and then afterwards kind of stop, and then have them kind of report out what did they observe, what happened during that activity, where are the photons now, who's ionized, who isn't. And some of the things that should come out is that no photons with energy more than about 25 electron volts should have made it to the ground. Right? So they all get stopped in the atmosphere. And then most of the photons, especially the ones in the range of 1 to 3 electron volts, they'll make it all the way to the ground. So the point of this model then is to show that the atmosphere itself is a shield against those high energy photons, and create the ionosphere so the ionosphere itself isn't so much the shield as it is the result of the atmosphere having been a shield for those high energy photons, right? Because when you look at where the high energy photons are absorbed, they're all going to be right near the edge of space, right? Because basically every single one of the gas particles was out there, they're going to grab a photon, any high energy photon, as soon as they see them. And then the low energy photons, unless they were the specific frequency that could have been absorbed by those gases, they make it to the ground. So they should see that, for example, visible photons, for the most part, they're just going to make it straight onto the ground. A lot of the infrared will also get grabbed up, but they're going to get grabbed up in the stratosphere by the water vapor, or by carbon dioxide and methane. So these are what the cards look like. So if you're a gas particle, you'll get a card that says your name and it shows your chemical symbol. They'll say where you're supposed to be located, and then it'll tell you which photons that you can grab. So, and I made these for the most common elements that are in the atmosphere, or elements and molecules that are in the atmosphere. Some of them I repeat, like molecular nitrogen, and I repeat them because they're more common, right, in the atmosphere. And so if you're going to make a whole bunch of these for a whole class, then you may want to kind of keep the proportions that are in the cards, right? So there are twice as many nitrogen as there are water, so that means that, when you run off a copy of these, make sure that you've got twice as many nitrogen molecules as you do water molecules in your classroom/atmosphere. Now, one of the things that was interesting about nitrogen was that when I was doing my research on this, I couldn't find any other, I know that it must absorb other wavelengths, but I couldn't, in the research I was doing, I couldn't find the other specific wavelengths that it could grab. So I only just left in all of the high energy things. Because as it turns out, most of what does the absorbing in the upper atmosphere is the nitrogen. And that's because it's the largest component of the atmosphere. Okay. And there's our nitrous oxide. Good old oxygen. Oxygen is also pretty common, so I put a few slides of it in there. Then the ozone. And then here's what the cards for the photons look like. Pretty simple. Just says infrared and then gives the energy in electron volts. And again, I tried to, there are more visible ones than there are infrared ones, and there are more infrared than there are, say, ultraviolet. And I think there's only one. So there's kind of relative proportions to give you the sense that when the sun is sending out the energy, most of the energy is coming in visible light, and only a little bit of the energy comes in the high energy photons. It's kind of fun to realize how energetic gamma rays are compared to visible, right? 1 million electron volts versus, 1 electron volt.
Brian, I have the video queued up of the activity. Do you
want you do?
Yep.
Sweet. You want to show that?
I can if you want to let me have
Stop sharing? Yeah, I'll stop sharing and you go ahead, show it. So we did this activity last winter at one of our workshops. And luckily, someone got video of it.
I did. All right, it's iPhone videos. It's not going to be great, but here we go. So I believe, so here's Lynn, and I think you've already given out the cards, Brian, and explained the activity. So they're getting all lined up, I believe, is where we're at.
Okay.
See, you're pushing me away.
Yeah, so those are the gas particles. Never there's the photons, so I'm giving the photons their instructions.
Kathy being gaseous.
Yeah, they're moving around being gaseous. There you go.
Are you just telling them what they?
Yeah, I think I must still be telling him. Yeah, I don't know if you want to skip ahead to the actual.
Yep, they're ready.
Oh yeah, someone said it is kind of like Red Rover, huh?
Get ready. You watch us for your all right, come on from the side. Come on, yeah. All right, show me your energy. So we have two visibles, and one ultraviolet faded through, and one visible tinge.
So they're talking about one of the visible photons decided to be funny, and she decided to bounce off the ground, and she went back out into space.
Where are my high energy photons? Where did you guys get to? Gamma ray, X-ray, and my ultraviolet. They got zapped. Okay. High energy guys, I stopped right here, right at the top of the atmosphere. Where does my infrared get stopped? Okay, who grabbed my infrared? Water grabbed my infrared. And so did carbon dioxide. So carbon dioxide. There were some wavelengths that I could grab. But you didn't. You weren't. Well, you didn't count for me. Okay, that's fine. I was there.
I think we probably stop it there. Yeah, so we had that discussion about what happened there. Like I was saying, one of the teachers decided that they would be clever because they were a visible light photon, and they bounced off the ground and headed back out into space.
Always fun to see that again. Chris is back. Do we want to ask him the question about the ham radio?
Oh yeah, Chris, there was a question that Vic was asking about ham radio, and we were discussing when the ionosphere is thicker, so when, say, there's maybe more solar activity, what's your experience as a ham operator? Do you have to, in order to to talk long distances, you have to change frequencies? What happens to your ability to talk over the horizon?
It's my understanding that the signal bounces off of the ionosphere, so it's no longer in line of sight. I've never really operated a radio myself. I have my license just because I was helping campers study to get their license, and we all took the test together.
Oh, okay. Yeah, you definitely have to use it for non-line of sight communications. You have to use the atmosphere. But yeah, it does change something. You know, what you have to do to continue talking to, say, a station that you were talking to over the atmosphere, over the horizon, will change. And so Vic had heard that you may have to switch frequencies, which sounds plausible to me. Okay, are there any other questions about ICON or the ionosphere? Up there, Vic's got one. There you go.
Here, I just was at spaceweather.com. They've got this one little activity where they're running the high stratospheric balloons up.
Uh-huh.
And they plotted the absorption of the high frequency waves as they go up in the atmosphere. And instead of a straight line, it looked either like it was a exponential or a quadratic curve on it. So that the higher you go, the doubling effect isn't proportional. In other words, twice as high, you get twice as much. No, it's worse than that. Because
mostly, I think that's probably because of the density. The density is not a linear. The density doesn't fall off linearly, right? So the density is falling off at some high function. So that's why you'd see an increase in high energy waves as you're going up. And you know what? There's I don't know if you probably all have seen the activity that's in the space science sequence, or it's in the old GEMS guide, the Living with a Star GEMS guide, the one where you do the pretend balloon mission and you send the balloon up and you collect the data from those different wavelengths. And it does show that it's not a straight line. It's kind of a curved increase in the amount of photons that you see. But yeah, that's actually really cool that they have some real data. That's so great. There's so many student groups that are now building these balloons that we got to get those data on online and be another part of our whole heliophysics story, right? You know what? There was one other thing I wanted to show you if I have time.
Yep, you can have about 5 more minutes,
Okay.
Or have it in a little bit more if you need.
Sure. I just wanted to show you guys the ICON website just so that you know where it's at if you're curious about it. And I think it's going to be updated, pretty soon. I know that Claire has been working with the team here to actually work on the public part of the ICON mission. So I think this is actually somewhat the older version because it still has this tab for outreach. And unfortunately, we no longer have an outreach. We no longer have an outreach or plan for the ICON mission. But you can get. Looks like Claire has actually been at least keeping up to date on what's happening with the mission here. So it looks like you can get updates on the mission's development on the front page. And so the URL is icon.sl.berkeley.edu. Can get still through the education portal here. You can get some useful information. In fact, I think it's probably under the For Teachers little tab here. Originally, our education plan was going to be to do some workshops in partnership with the Stanford Solar Center, which, by the way, they're kind of going away. So you should check out their website soon. But they have been for several years. They have created educational guides. Oh no, that link doesn't work. All right. So the thing to do, of course, is to do Stanford sudden ionospheric disturbance. They're called SID monitors. And so what these are really simple devices, and you can actually, Stanford no longer makes them. So I think even though the Solar Center is shutting down in a little shortly here, you can still get them from, I believe it's an amateur astronomy group that's now building these monitors. And you can download the information here about what to do once you actually get a monitor. But what these are is they're basically just radio antennae that are that get tuned to a frequency that the Navy uses to communicate with submarines. And so it's communicating over the horizon. So it's using the ionosphere to bounce its signals. And these they have antenna all around the country. So you set up, actually all around the world. So they have transmitters that are transmitting their signals, and you can create an antenna that will pick up the signal, and you can measure the strength of the signal, and the strength of the signal will wax and wane with the ionospheric strength. So you can see the daily signal, for example, of sunrise and sunset, when the ionosphere is getting really strong during the day and when it's getting really weak during the night. And then you can also see solar flares. So whenever a solar flare goes off and it deepens the ionosphere, you can see that signal in the signal that you're picking up with your antenna. And so all this is just a radio receiver that's tuned to that frequency that the Navy uses. And then there's some software that allow you to plot up the signals and save the data that's coming through on that. It's really similar in notion to Radio Jove. Are either of you familiar with Radio Jove? It's the same idea, except it monitors Jupiter on a radio frequency.
Lynn's involved with that.
Yeah, and the same thing happens with that. Basically, any radio waves that are passing through the atmosphere are going to be attenuated by the ionosphere, and if the ionosphere changes due to space weather, you'll see that signal. I think the signal is stronger in the SID monitors than it is in the Radio Jove. So the SID monitors end up being a great solar flare detector. So it's a pretty neat thing that you can do in the classroom. Use it as a solar flare detector and monitor the strength of the ionosphere. Okay, so that was the last thing I wanted to share with you.
Well, thank you so much, Brian. This has really been extremely informative for us, and really great ideas and on how to bring it to the, because Laura has the chat here about how she likes the analogy about the boiling water, and I have to say that was really helpful for me as well when you first explained that to hear it. So thank you so much for sharing about that tonight. And I'm assuming that you will put your stuff up on the Wigio so that people can go back and look at it.
Yeah, I'll put everything I can on the Wigio. Try to do that right now. Oh, awesome. Let me mention that analogy I had about heat and temperature. I actually have an activity where you can have your students do an at-home experiment where they melt ice cubes in the oven and in the boiling water, and they time how long it takes. It's two experiments. They do first, the boiling water in the oven, so you got two different temperatures, and then you can do it in 2 cups of water that are at room temperature, right? So you have one's a cup of water, the other is just a cup of air. You let the water come to room temperature, the air is at room temperature, put the ice cubes in, and again, time how long it takes them to melt. They melt faster in the water than they do in the air, because even though they're at the exact same temperature, there's more thermal energy in the water because there's a higher density of particles. So that activity is, I'll put that in the chat where you can get that. It's on NASA Wavelength from a mission that I had worked on years and years ago called CHIPS, that was about the interstellar medium, and we were trying to explain how it can be that gas with such low density can have such high temperature.
Perfect. That's awesome. If you wouldn't mind also putting on the Wigio in your post, Brian, then it can get there faster to the, I'll have the chat and I can put it up later too, but if you can go up there. So any last questions for Brian or about ionosphere or icon or any other things that he presented tonight? Make sure that I can see the chat in case Laura has something. Well, I know so many people had things going on tonight, and I'm sure that that they'll be checking out the video later. Hopefully, we'll have more folks with us next month. We do. Oh, perfect, Brian. Thank you. So the NASA education team does need to make you aware of a situation. And as many of you know, that that we had in our work, our work is as the NASA EPO forums were coming to an end, and we had our funding issues a couple of years ago, as Brian was talking about, where education monies were taken out of missions and outreach money were taken out of missions, and they've allowed us to go forward in the last year. But in this next cycle, we had made proposals to which this group was part of one of those proposals. And our proposal that Brian worked very, very hard on was not funded. And so we are needing to consider about, there were heliophysics proposals that were funded. And I know that there is an interest in continuing work very similar to what you have all been engaged with us in the last 3.5 years or 3 years with us. And so I don't want it to sound like this is going to die or that it's going to end permanently. I know that Ricky and Brian and Don and I will be talking very hard about how to make sure that what is in place before December. Which is when our time will, perhaps more than likely, December may be our last meeting as far as how we're going forward in this conversation. So we will keep you posted on what that means. The Wigio is not going away. Zoom is not going away. We are very steeped and have a vested interest in continuing this group. So we will make it available somehow. And as we search for what that conduit and pathway is, we will most definitely be keeping you in the loop about how we can go forward together and where those places might be. So I'm looking forward to hearing from some of the other Helio proposals that were funded, and to see how we can partnership together to make sure that you aren't, that you can carry on together as a group. Anybody have any questions about that, or? All right, well, on that note, we will have a meeting next month on, I believe it is on the 20th, November 20th. Wait, today's the 20th, so it's November 17th, I believe. Is that what I said at the bottom of the agenda? November 17th is our next meeting. I know that Don Turney has invited another mission specialist to come and speak with you. And they will come with some resources as well, and we will have more information about how we will be continuing to meet together in the future at that time. So I hope to see you guys November 17th. It's Tuesday before Thanksgiving, so hopefully more people will be able to make it that week. And then we look forward to seeing you guys then. So thanks for joining us.
Bye.
Goodbye.
Good night.
Good night.
Good night.
Yep, you too, Laura. You can stop the recording, Ricky.